All right, still another attempt at agent. Wasn't really satisfied with the random search and rotation. Was kind of went off all over the place. What I have now, I want to change into an algorithm for finding how to move. So I feel like we're not going far enough. So we should try, if we can, to go forward. And so if we've reached a certain point that we said we could satisfy all our conditions, try to go forward a little bit more by casting that forward maybe another 6 meters, 5 meters, 3 meters, 2 meters. If that doesn't work, then try going to the right, starting with 90 degrees to the right and 6 meters, 5 meters, 4 meters, 3, 2, and then maybe 80 degrees at 6 meters, 5, 4, 3, 2, etc. until you end up at negative 90 degrees or maybe even negative 180 degrees relative to your current position. So let's give this a try. Agent. The other thing I changed was we need to separate the dumb agents from the smart agent. So this set interval is intended for the smart agent. It's just seeing if you suddenly become the leader. So it should be a no-op most of the time. So it only kicks in this update function if you're the leader. So if you're the leader, it will look for a place to go to and send that message to everybody. And then the rest of the time, you're dumb. So you just receive the member movement and you should not send anything into that event bus. This is where I had it wrong, because then you become a leader too if you were to do that. So don't do that. Just move yourself. And the go-to function is what moves us, and the go-to function should also not send anything to that bus unless we are the leader. So here I added this. If we're the leader, when we're we can detect things like, oh, am I running out of floor? Which shouldn't happen because the point that I'm casting to definitely did not run out of floor. But I suppose it can happen if somebody removes some floor. I guess that's certainly possible, but we can make this check secondary. Don't know if that really helps or not, but yeah, we want to check if something's in front first. It's probably more likely to happen, so we don't need to waste time on this one. Okay, so then this one can cancel, which will just cause us to go to a stop until the next interval update is called on the leader. And okay, now we need something else. We need to update our random point or null. Okay, so let's update this function. Right now, it's 2 for loops. One to check a buffer distance, and one to check degrees. So maybe we have enough helper functions to do this. Let's see what helper functions we have. We have convert a direction to a coordinate. So we get a direction and a length, and it'll give us a coordinate. So this is pretty good. Let me maybe cancel some of this out. So what we want to do is we want to start with 0, number of degrees in front of us. So for loop, start with 0. So for, well, let's just say let degree equals 0, and then we want to check the distance. So let distance equal, start with 6 meters then. So for let distance, I guess this can be max distance. Anyway, let distance equal, start off with 6, and as long as the distance is greater than or equal to 2, then we can subtract distance. So we'll go from 6, 5, 4, 3, 2, and we'll check all of these. So this convert direction, so the degree is degree, and the length is distance. If this distance gives us a test point, and this is a point on the floor, right? We clone the position, and so we can just do, or copy from this transform position. The ray direction we can copy from okay. And then we want to rotate this to the degree in radians, and then temporarily transform this, and then copy the direction from that direction after it's converted over, and then we set the ray length, and then we push it over a bit. This transform position clone, what is this doing? Add this ray direction scale. Oh no, we just want to move that origin over. Convert direction to a coordinate. Let me see what this does actually. Return this ray for fun. Oh, wait. Add. This returned a vector 3, which was the position. Oh, you took your position of where you were, and you added the direction for a certain scale. And that tells you where the end of the ray was. don't think we need to do we need to add? What does this do? Add, it gets a new vector. Okay, so this doesn't add in place, so we can just do get position add this ray direction. Scale by length. I think this might be longer than it is. So let me just see what this does to paint the paint the ray. Let me let's see, what is this red? So random point. So random point doesn't return anything right now. Right. Let's return something. Let's comment out this bit. Should be fine. Random agent. What do we want it to do? We want it to convert. Convert what? Direction to coordinate. Direction to coordinate. Degrees. Let's say 45 degrees. Distance of 5. Alright, so if we just said random agent ray, what's your length? 10. Okay, so it didn't take into consideration the length I gave it here. Ray length becomes length. Okay, that seems about right. That's where you want to end up, 45 degrees, that way. How about 90 degrees? That works. So it looks like it's working here. So we want the coordinate though. And so the transform position. Let's see if what's the output? The output here is x is 5, which is right, y is 0, and z is a tiny number. So I guess that is correct. It's all 5 there. Okay. I think maybe we need to normalize. So normalize is an in-place operation. So maybe this one we want to clone the normalize and scale. And the result here should be the same though. So if we go off to the side, yeah, 45 degrees. Okay, so I guess this is fine. So we convert this there. So the test point, we have a test point, and we want to so wherever this direction is, this here is returning a test point. Convert to coordinate. But since it's at an angle, we can just give back a, we don't need a vector 3 yet, right? Convert. I guess this is fine. Then we want to test these two things. So if both these things are true, then this point is eligible. So let's say is point eligible, and give us a vector 3. Test point is a Babylon vector 3. Okay, so check the ground height, and so let test x equal test point x, and then let test z equal test point z. So if it's on the ground, you get a ground height, and if there's no obstacles on the way to this place, then return this new value, checkpoint eligible, otherwise return null. Okay, so here we'll do let checked point equals this check point eligible with a test point, and if checked point, then return checked point. Otherwise, it'll count down to the next distance, next distance, next distance until you get to 2, and then it'll exit because you can't go forward. So let's try to go to the right. 4. I guess we don't need this. Let degree equal, go to the right 90 degrees. And as long as degrees is greater than minus 150 degrees, go to the right, check, 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 check. And you can do degrees deduct yourself by about 15 degrees every time. Bam, bam, bam. Testing, testing, testing. And then inner loop, we'll also check distance. So we'll go, this one, can I go, can I go further in the distance? Go 6 meters at a time, maybe more. What's this? Oh, we do need degree. This one is just 0 though. Okay. This one is going to be degrees. And distance, yep. And then checkpoint, yeah. First one you find, you're going to return that one. Otherwise, you're going to return nothing. Okay, so let's see how this behaves now. So let's turn this back on. It should prefer to go straight whenever it can. If it can't go straight, it should go to the right. Keeps going straight. You can go straight. Now it goes to the right. It goes straight. Keep going straight. Whoa. So this one turned all the way around. Why didn't it just turn to the right, I wonder? So it'll just keep going around at right angles. It won't ever enter the space. So maybe, okay, so that's interesting. That was the one, current rotation, and then the rotation. Because of this current rotation, yeah. Okay, I think the reason why it spins around like that is because of we keep adding into y, and it kind of goes beyond one circle. So when you say set it to this many degrees, it has to unwind itself. Okay, so how should we fix this? Maybe we should make the rotation somewhat random. So I like the part where we go forward as much as we can. Null. Okay. So occasionally we can go forward. So pick between two different algorithms. So this one can be try to go forward. The other one is try to go some angle. Okay, so let's do, or maybe after you've gone to the right a number of times, you should start going left. Okay, so we can call this try to go forward, and we'll cut this and paste this here. We'll return null, and we can pass in the max distance to check. Set this to max distance. And this one is find turn to the side. Starting degree is a number, and max distance is a number. This is a number. And then we can put this in. And we can say that this is our starting degree. And then as long as degree is greater than half a circle away, then we subtract that, check the point is eligible, and then otherwise return null. And so now that we have two algorithms, we can choose between these two. And we can also seed this with a different degree between, let's say, 0 and 90. So we can say math random, and this will give you a number between, okay, so if math random is greater than, let's see, 50% would be around here. Most of it will be here, so 70% of the time it'll be this. So 70% of the time we'll try to go forward first, which is this, try to go forward. Let forward point equal this. If no forward point, then try to go to the side. Turn to the side. And starting degree will be math random multiplied by 90 puts a number between 0 and 90, so plus maybe 15 or 5. Turn side, distance is fine, distance can be 6. Try to return that. Else, rest of the time, don't try to go forward, just return to the side. Attempt to turn to the side. Again, it's at random. And maybe do go 90 degrees. Alright, so some of the time you're just making right angles, and the rest of the time you're trying to go straight. And when you can't go straight, you will pick some random little angle to go to. I don't know, let's see how this behaves. Just went to the right. Couldn't find a place to go most of the time. It's there, and that's off. Interesting. Can't find a place to go, can't find a place to go. What do you mean can't find a place to go? You got plenty of places to go. Try to go forward. Let's say can't move forward. Console.log can't move forward. I find that hard to believe. And this one says console.log can't move to the side. Where does it say can't find a place to go? Can't find a place to go is here. Okay, so if you find a point, random point or null, which is here, try to go forward, go to the side. Else, so this should never be called. Period, can't find a place to go. I keep saying can't find a place to go. So we must not be returning the right thing because it keeps saying can't find a place to go. We need to return a point. So try to go forward. Are you returning a point? Checkpoint eligible. It should never just say can't find a place to go. Why is it saying this? If there's a random point, then you create a movement. Otherwise it's saying distance of new point. Distance of new point. Okay, forward point. Let's try to go forward. If there's no forward point, okay, what's the forward point? Console.log forward point is forward point. That seems easy. You should find a forward point. Forward point, and it said can't find a place to go. Forward point. Yeah, it was here, and then it said can't find a place to go. Console log, no forward point, looking to the side. Oh, we didn't return the forward point. If forward point, yeah, let's do this. If forward point, return forward point. Otherwise, return this. That should fix it. Okay. I'll continue forward. 30% of it for most of the time. %70 of the time you'll move forward. Okay, that must have been the 30% of the time you just decided to turn. And how does this fare with another browser? It's pretty good, except that twisting, turning around thing. Seems like eventually they start going around in circles on the left. So what if we made it 50% of the time you'll go straight, then 25% of the time you'll go right, the other 25% you'll go left. Turn to the side, you can say starting degree, ending degree, you're always starting with something positive, sweeping negative. So if you just say starting degree, ending degree, and but the operation is either greater than or less than. So if you start off sweeping from the left, it'll have to be greater than it'll have to be less than. Starting degree has to be less than or whatever. Right? So I don't know if I can make this into a generic function. This is turn to the right. This is more like scan from the right. Scan from the right, scan from the left. Starting degree, and scan from left. Would be starting degree is here, and it's going to be less than that. You'll add some degree to it. So go the other direction. Starting in the negative, let's say negative 90, go up through 0, and then go to the right. So then, let's say 50% of the time, try to go straight. Otherwise, just scan from the right. If you can't go forward, math random. Yeah. Else, so let's say let rand is math random. Else, if rand was less than 0.25, then we'll scan from right in the right, else just return this scan from left, negative 90. Okay, so most of the time you want to go straight, except if you can't go straight, go to the right, some random degree. Otherwise, 25%, you try to make an absolute right or an absolute left, the other 25%. Time. How does this look? Okay, made it to the right. Oh, random. Oh, nice left. Nice left again. And left again. Okay. Now, what are the other kinds of animation? So, animation that we're doing is Babylon animation constant. What are the mode was there in? There was a, oh no, it is constant, but we have an easing function, right? Let's see, Babylon JS animation easing function. Easing function. Bounce ease, sine ease, Bezier curve ease. Babylon circle ease. So slow and then fast. And this is cubic ease, elastic ease, exponential, quadratic ease, sine ease. Okay, let's just do cubic ease. Babylon cubic ease function. New. Does that work? New Babylon cubic ease. I guess that's how you use it. Select localhost. What is this book, by the way? Web development. Didn't tell you what book it is. Anyway. Slow, fast. Slow, and sudden stop. Okay, I don't really like it. I'd like a ease in and ease out. Is there one with like a bump in the middle? Babylon JS easing function ease in and out. Easing mode, ease in and out. Set easing mode. Okay, so let's say let ease equal new Babylon cubic ease dot set easing mode Babylon easing or pretty good. I mean, it's a little bit off to a slow start. What other easy modes are there? I mean, elastic ease, bounce ease, back ease, circle ease, power ease. Hmm. power of the function. 2? What does this take? Two times 4. Ooh, it's even slower. 0.5. Oh, it's so slow on the ease out. Oof. That's some strange behavior. How about that cubic ease again? And what are the parameters? Dot ease set easy mode. Not a lot. Let's just set this to no. Nothing's better than what we have right now. Maybe our just our traveling time is just a little slow, but I think it's fine for Monster. What else? So I think this is pretty good in terms of, yeah, let's give it a wall. One more thing. So if we trap it in a wall, we go do, whoops, reset, bam, 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 build. You're stuck in there. Got out. And it's not likely to go back in. Unless it does that. Okay. So the whole turning thing is something I gotta fix. We'll do that for next time. Fix the intent to spinning around business.